All right, Unit 5, kinetics to review. So kinetics, you guys know what kinetics is. It's the study of reaction rates. Oh, it would help if my pen was working. Study of reaction rates. And we care about reaction rates for tons of different reasons, right? Like we want to know how long is it going to take for a medicine to, activate in our bodies, or how long is it going to stay in our systems. So like metabolism is really important in determining reaction rates for medicines. Other important reasons is like if we're actually trying to produce something, if we're trying to make a vaccine, or if we're trying to make an alloy to build a building out of, or we're trying to make ammonia for our fertilizers, any of these reactions take time. And so we want to know how long do they take and how can we affect their reaction rates. And reaction rates are governed by something called collision theory. And collision theory basically just means that for a reaction to occur, molecules have to collide. They have to hit one another. So the reactant molecules have to collide with two key factors. So a good collision has to have enough energy to overcome the reaction's activation energy. And the collision also has to happen with the correct orientation. Meaning, like if you want to form a bond between hydrogen and oxygen, the hydrogen atom has to hit the oxygen atom. So those molecules have to collide with that correct orientation. And those were the examples where I was always showing you, like, remember how I was like putting together, if I wanted to make a Halloween molecule, like the black marker had to hit the orange marker with the proper orientation to stick together. So that's what I mean by orientation. Okay. All right, so the more effective collisions we can make, the faster the reaction will happen. So if you increase the number of effective collisions, then you will increase the reaction rate. And so there's a couple of factors that can do that. Like there's a couple of things that we can do to reactions to increase those numbers of effective collisions. And if you guys remember, this is where I used the sex example, which made everybody super uncomfortable. So how do we increase those numbers of effective collisions? Oh, geez, my screen is going crazy. So factors that will affect rate. Number one is what we call the nature of the reactants. Two things we mean by nature of reactants. We mean states of matter and surface area. So solid, liquid, gas, and aqueous. These states of matter up here towards the top, like gases and aqueous, those states of matter have greater surface area than solids do. And so when you've got an increase in surface area, you've got more places for those collisions to occur. So when you increase the surface area, you will increase the number of effective collisions, and thus you will increase the reaction rate. Okay, so that's one thing that can affect rate of reaction. Another thing is concentration. If you have a more concentrated sample, a more crowded, like if I'm imagining, one sample has just 2 molecules in it versus another sample where you've got 4 or 5 molecules in it, you're gonna get more collisions the more crowded the area. So when you increase concentration, or if you're thinking about gas phase, that would be like an increase in pressure, you're going to increase your number of effective collisions. And thus you're going to increase the rate. We can also affect rate with temperature. Because think about it, if you've got a sample with 2 molecules of gas and you have another sample with 2 molecules of gas, but this one's at 25 degrees Celsius and this one's at 100 degrees Celsius, these molecules are moving around a lot faster. And so they're gonna collide with each other more often. So when you increase temperature, you increase the speed of the molecules, and so you will increase the number of effective collisions. And not only will you have more collisions, but you're going to have more collisions that have enough energy to overcome the activation energy. So like temperature is one of those ones where not only are they colliding more often, but more of those collisions are at a faster rate, or I mean, it's not a faster rate, are hitting each other harder. And so more likely to overcome the activation energy. And then the last factor affecting the rate would be catalysts. And a catalyst will lower the activation energy. And if you reduce that energy barrier, now more of your collisions will be able to overcome that barrier. So when you decrease the activation energy, you are going to increase the number of effective collisions and thus increase the rate. So those are our 4 factors: catalysts, temperature, concentration, how fast can you write, states of matter. Don't forget, you guys, I'm recording this and I'll post it, and I'm also going to send you guys the image of it so you don't feel like you have to keep pace, but I do want to make sure we get through all of it. So that's why I'm going so fast. Any questioners, any questions on factors affecting rate? Okie dokie. Let's talk about how we measure rate. Ugh, I gotta move this out of my way. Come up here. Ah, there we go. Okay. How do we measure reaction rate? We can measure rate by looking at changes in reactant or product amounts over time. Right? So like if I've got, you know, reactants A plus B making C and D, I know that the concentrations of A and B are going to go down over time, and the concentrations of C and D are going to go up over time. And I could measure either of those things in order to measure the reaction rate. Now, let's say I had the reaction 2A plus 1B makes 3C. Okay, like let's just say that this is my balanced equation. If I was talking about the rates at which A and B are disappearing, A is going to disappear twice as fast as B. Because for every 1 molecule of B that gets used up, I'm going to use up 2 molecules of A. So remember, these rates do depend on these coefficients. So if I wanted to compare these rates to each other, I could say that -1/2 the change in concentration of A over time is equal to negative change in concentration of B over time. In other words, if I wanted to set these two things equal to each other, I would have to have the rate of A, because it is disappearing twice as fast as B. So to set them equal, I would need to divide this guy by 2. So you can either look at it as like 2 and A is 2 apparently. I could look at it up here in terms of A is disappearing twice as fast as B, or I could set them equal to each other by dividing by their coefficients. And remember, these negative signs are here, you guys, because reactants are disappearing, and we don't ever want rates to be negative values. So because these would be final minus initial, we have to multiply by a negative to report our rate as a positive value. We don't have to do that over here for substance C because C is appearing. So the change in concentration of C over time will be a positive value on its own. Okay, so substance C is going to be appearing 3 times as fast as substance B is disappearing. So we can compare the rates of the disappearance of the products and the appearance of the, nope, I said that backwards. We can compare the rates of the disappearance of the reactants to the appearance of the products by looking at those coefficients, okay? And it could be change in concentration, it could be change in pressure, it could be change in pH, it could be change in volume of a gas, it could be change in mass. Like, it really could be change in anything, you know, anything that can measure amount over time, okay? Now, if we're looking at this graph that I've got right here, you guys, this is showing concentration over time. And what you can see is that this reaction is slowing down over time. Do you guys see how the slope is getting less steep over time? So most reactions slow down over time. And that's because, like we talked about earlier, concentration affects the rate. So as the concentration of the reactants goes down, the reaction is gonna slow down. Okay, so most reactions slow down over time. The ones that do not are called zero order reactions. Zero order reactions have constant rates. Like they just whoop, same rate the whole time for zero order. But for everything else, for first order and for second order reactions, they're gonna slow down over time. So there's 2 different ways to measure rate. You can measure average rate, like we do up here, just, you know, pick 2 points in time and, you know, subtract those concentrations and subtract those times and divide. That's, oops, I forgot an average. There's an E in average. Average rate. The other way that we can calculate rate is something called instantaneous rate, which is the rate at a certain point in time. Instantaneous rate, to get the instantaneous rate, like if you wanted to know the rate of the reaction right at the beginning of the reaction, you would do what they're showing up here, which is you take the slope of the tangent line. Okay, so you take the slope of the tangent at a certain point in time. So this, you know, if I wanted to know what the instantaneous rate was at 5 or what was this, 6 seconds, I would draw a tangent line at that point in time and take the slope of the line right there. That's the rate at that point in time versus an average rate, which would average all of those rates together. So in the lab that I'm gonna have you guys look at tomorrow, you're gonna calculate the instantaneous rate at the start of the reaction by taking the slope of the tangent pretty early on in that reaction before it slows down. Okay, so average rate is over a course of, I don't like how I smushed all these together, sorry. Average rate is over a course of time, instantaneous rate is at 1 point in time during the reaction. Okay. Everybody all right? Okie dokie. Let's talk about how we determine rate laws. So what I was referring to here, you guys, this whole idea that concentration can affect the rate, how much? Like how much does concentration affect the rate? If it doesn't affect the rate at all, we say that the reaction is zero order. If it affects the rate a little bit, then we call it first order. And if it affects the rate a lot, we call it second order, and so on and so forth. So like these reaction orders are a measure of how much does the concentration affect the rate. And we call that the rate law, okay? So the rate law expresses or quantifies how much concentration affects rate. And they always take the form of rate is equal to K. Remember, rate is your, what you're measuring, change per, in concentration per unit of time, equal to this rate constant K times whatever the reactant concentration is raised to some exponent. Okay, so this would be, one of the reactants that we were looking at. These exponents have to be determined experimentally. Okay, so like those exponents are not coefficients. Okay, they are determined by experiment. And there's two different types of experiments that we can look at. We can do an experiment where, as we see down here, we can do an experiment multiple times. Okay, so you can see here in this setup, we're doing multiple different experiments. And in each of these different experiments, we are messing with or changing the concentrations of the reactants. Okay, so this is an example of running multiple experiments with different initial concentrations and looking at how rate was affected. So, in order to do these types of problems, remember, you're going to look for where, in this case, we have 3 reactants. Okay, so we're trying to find the rate law for all 3 of those. So we want to find out how much does the bromate ion affect concentration, or how much does that concentration affect the rate? I'm sorry. How much does the bromide ion affect the rate? And how much does the hydrogen ion affect the rate? So I want to find all 3 of those exponents. So what I do is I look for a place where 2 of those reactants stay the same and where one of them changes. So if I compare experiment 1 to experiment 2, where's my pen? Come on, wake up. Jeez. Okay, there we go. All right, experiment 1 to experiment 2. Do you guys see how from experiment 1 to experiment 2, these guys stay the same? Right, the bromines and the hydrogens stay the same. And this guy gets multiplied by 2. What happens here to this rate? Is that times 2? 1.6. Are you guys calculating along with me? Are you still awake? It's times 2. Yeah. Oh, thanks. Was that Chinito? Okay. So if when I double this guy's concentration, I double the rate, that means that this guy's exponent is a 1. That means it's first order, right? So if I double this thing and the result is a double, I must have raised it to the first power, right? That's how I get that exponent. Let's look at what happens in another experiment. Okay, so like let's look here where the bromates stay the same and the hydrogens stay the same. And we double the bromide. When we double the bromide, what happens here to the rate? So 3.2 divided by 1.6. That's another doubling. It doubles again. So when this substance is doubled, the rate is doubled. So that guy's also first order. And then our last one, what are we going to have to compare here? Okay, experiment 1 to experiment 4. See how that stays the same? And that stays the same. And what are we doing to the hydrogen? We're doing the hydrogen times 2. What happens to the rate? So 3.2 to the negative, oopsies, 0.2 divided by 8. -4, it quadruples, okay? So here, the rate gets multiplied by 4. So what would my exponent have to be? My exponent would have to be a 2 in this case. So that one is second order. So it's second order with respect to the hydrogen. Okay, so my rate law would be equal to K BrO3 minus raised to the first order, second order. And we would say that this reaction is fourth order overall because we would add up all of the exponents. So fourth order overall. And then of course we could actually calculate the value for the rate constant. We could just plug in the concentrations and the rate and we could solve for the rate constant. The rate constant is going to have different units depending on what order the reaction is. So don't forget about that. And I think that's all I wanted to say about that type of a problem. Okay, so that type of problem helps you determine rate by running multiple different experiments with different initial concentrations. There's another way, though, to figure out rate law, and that is by running one experiment and watching it change over time. Okay, so this experiment, there's another method. Another method to determine rate law is run one experiment to completion and look at how concentration changes over time. Concentration and rate change over time. Concentration and rate change over time. So this is one of those ones where we make 3 graphs, right? So like I would make this first graph. I would make a graph of concentration versus time. If the concentration versus time graph is linear, meaning the reaction does not slow down over time, I would know that the reaction was 0 order. Because that means that the reduction of concentration over time didn't affect the rate. However, if I were to graph concentration versus time, and I saw the reaction slow down, like I saw a curve, it was not linear, that means that it's going to be first order or second order, because both of those are going to slow down over time. And the question is, well, which one is it going to be? And the way that we can figure that out is we can integrate the rate laws and make 2 different graphs. If we graph the natural log of the concentration versus time, and it's linear, then it's first order. If we graph 1 over the concentration versus time, and of course we're going to get an increase there, then the reaction is second order. You guys remember that? So I think where did I put? Oh, I didn't. Oh, that's sad. I thought I had a nice chart with everything in it. I didn't. That's why I was squishing it all into one place. Okay, so I'll just squish it in here. Okay, so there's a couple of things that you guys need to know. Remember we made a cheat sheet? Do you guys remember we made those we made those kinetics cheat sheets with all of this information and all of those equations? I would have that handy, like when you're taking the actual AP exam. So if we were to integrate these rate laws, like the rate law for a 0 order reaction, the differential rate law would just be rate is equal to K. Rate is constant. That's for 0 order. That's what we call the differential rate law. For first order, your differential rate law, rate is equal to K times, one of those concentrations, like let's say Ka, raised to the first. This is your first order differential rate law. And if it's second order, it's going to be Ka squared. That's your second order differential rate law. If we were to integrate these things, which is just calculus, you get an equation that allows you to look at how rates and concentrations change over time. And I didn't leave myself enough room. I'll just write these in a different color. The integrated rate law for zero order looks like this. The concentration at any given point in time is equal to K times T plus, negative KT times the initial concentration. This is my integrated rate law for zero order. And what you guys should be seeing in that rate law is Y equals mx plus b. So like if I look up at that graph, on my y-axis is just concentration. On my x-axis is time. The slope is equal to, and it's a negative slope, so this negative times that negative gives me a positive rate constant K. So the slope of this line is how I can get my rate constant. And of course, my y-intercept is whatever my initial concentration was. So I know that if this line is linear, it's going to be a zero order reaction. I can also integrate my other rate laws, and it allows me to actually calculate what the concentration is going to be at some other point in time in the reaction. It allows me to predict how much stuff I'm going to have at a certain point in time. That's the beauty of the integrated rate laws. So the integrated rate law for my first order reaction would be the natural log of the concentration at some point in time is equal to negative KT plus the natural log of my initial concentration. And you can see the y equals mx plus b and how that lines up with this guy's slope, negative K. Let's see if there's a question. Yes, the first integrated rate law was only for zero order. Yep, exactly, sorry. So this guy's integrated rate law, this guy's integrated rate law, and 1 over the concentration at some point in time is equal to KT. This one's positive because we have a positive slope here, plus 1 over the initial. So if you are ever asked to make a prediction about what the concentrations are going to be some point down the road in a kinetics problem, you are going to go to your integrated rate laws. Now, the other thing that these rate relationships can tell us is the half-life of a reaction. So if I wanted to know, like, how long does it take for my initial concentration to go to half of its initial amount, I could calculate half-life. And there are half-life equations for all different orders of reaction. But for some reason, the AP test's favorite little factoid is that the half-life of first order reactions is constant. So the T1/2 for first order reactions is constant. That's just a feature of first order reactions. Like nuclear decay reactions, their half-lives are constant, and they're the only ones that are constant. So the T1/2 for a first order reaction is 0.693 over K. This is the half-life equation only for first order. We could write out the half-lives for the other ones. They're not important. Like this is the fact that they just sort of love to harp on for some reason. So like nuclear decay, for example, nuclear decay is first order. Their half-lives are constant. The time that it takes to go from 100 grams to 50 grams is the same time that it takes for 50 grams to go to 25 grams, which is kind of interesting because you would think that it would take longer for, bigger amounts to decay. And, for 50 to be lost versus 25 to be lost, you would think that this would take longer. But in first order reactions, it doesn't. The half-life is constant. Okay. And, ooh, I think we're doing okay on time. The last thing I want to talk about, you guys, is, oh no, not the last thing. Sorry, I have 2 more things to talk about. Are we doing okay? Hopefully. Hopefully. Yeah, C. All right, that's all about how concentration affects rate. Okay, 2 different types of experiments we can do to determine how concentration affects rate. So we just looked at number 2. We did this. And hopefully some of you did a little, nobody really did the demo. This was the demo that you guys were supposed to do that nobody did because nobody had any Alka-Seltzer tablets. The next one we want to look at is how temperature affects rate. You could have done that with the Alka-Seltzer tablets too. So let's look at how temperature affects rate. The way that temperature affects rate is twofold. There are 2 factors. There are 2 factors that affect whether or not a collision is effective, right? First of all, they have to have enough energy to overcome the activation energy, and then they have to have the correct orientation. And both of those things can be combined, and we're not going to do the derivation here, but I just want to, because it's a review, I just want you guys to remember that this rate constant depends upon the number of collisions that have the correct orientation, that's this factor A, times e to the negative EA over RT. This is called the Arrhenius equation. And all it's showing us, oh, yep, variable A, yep. Let's define our variables. Oopsies. Come on, pen. A is, this is called the frequency factor. And it is a measure of collision orientation. Like how many of the collisions have the correct orientation. It would be a constant for a particular reaction at a particular temperature. And this factor here, the e to the negative EA over RT, this indicates how many collisions have enough energy that is greater than the activation energy. Okay, so this is the one that looks at how many of those collisions have enough energy to get up over that hump, that energy barrier. Yep, and the R is your energy R. So when we use this equation allows us to look at how temperature and activation energy, those are the 2 factors that are going to determine whether or not a collision was effective. Okay, so whether or not they have the correct orientation and whether or not they have enough energy to get up over that barrier. And so this R is our 8.314. That's our energy R. Okay, so think about it. If we increase the temperature, we are increasing how much energy those collisions have. And so they are more likely to have enough energy to get up over that energy barrier. We can also integrate this rate law, or not rate law, but we can integrate this equation. And when we integrate it, we get ln of K. Sorry, hang on, there's a chat question. Temperature must be in Kelvin. Yes, because this is joules per mole Kelvin. So your temperature has to be in Kelvin. Okay, so when we integrate this rate law, we get ln of k is equal to negative EA over RT plus ln of A being that frequency factor. And I know that looks like a pretty gross, icky equation, but we're gonna actually use it in the lab tomorrow, or the virtual fake lab tomorrow. If we were to make a graph of a bunch of different, so do you see the y equals mx plus b? Y equals mx plus b. If we were to graph the natural log of the rate constants at a bunch of different temperatures, 1 over t, see the 1 over temperature is on my x-axis, 1 over t. If I were to make a graph of this, the slope of this graph, the slope of this line, the slope would be equal to negative EA over R. In other words, I can run a bunch of trials for a reaction at different temperatures. And when I increase the temperature, I'm going to increase the rate, and I'm going to get an increase in the rate constant K. And when I do that, if I measure these different rate constants at all of these different temperatures, and I make this graph, I can calculate the activation energy for the reaction. Like, if you're ever wondering, like, how do scientists figure out what the activation energy is? Like, you're telling me that this reaction needs 450 joules in order to occur. How do we know that? Well, this is how scientists actually figure it out. They run that reaction at a bunch of different temperatures. They measure the rate constant at all of those different temperatures. And from that, you can calculate the activation energy of the reaction by looking at the slope of that line. Okay, so that's what the purpose of integrating the Arrhenius equation is, to calculate activation energy. Aren't people so smart? Scientists are so smart. Like, who figured all this out? It's hard enough just to explain it. Imagine imagining it up on your own. It's wild.
I did.
Good job, Justin. Yay, Justin's awake. All right, last thing. Last thing, I promise. Reaction mechanisms, okay? What if a reaction happens in multiple steps? Mechanisms. You're used to seeing reactions happening in one step. You're like, oh yeah, like there's my activation energy. Got to get up over that hump, right? This would be a one-step mechanism where your reactants go up over that activation energy barrier and they turn into products. This would be an example of a one-step exothermic reaction. But what if that reaction happens in multiple steps? What if you have a potential energy diagram that looks like that, right? Where your reactants do not immediately turn into products, where your reactants turn into first something down here. These are called intermediates. And then those intermediates have their own activation energy before they turn into products, okay? So here is activation energy number 1. We talked about this a little bit earlier in the week. This is EA number 1, and this is EA number 2, activation energy number 2. Which activation energy is bigger? Clearly, step 1 of this particular mechanism has a higher activation energy. If step 1 has a bigger activation energy than step 2, it's going to be what we call the rate limiting step. That's our slow step. So the reaction is only going to happen as fast as this first step does. This second step is happening a lot faster. So whoever has the bigger activation energy is the rate limiting step. We very well could have had the second step being the slow step, right? Like we could have had a diagram that looked like this. Here, the second step. So here's my reactants, here's my products, here are my intermediates. Here, this activation energy is much bigger. So here, step 2 is the slow step. It limits the reaction rate. Okay, now the very, very last thing is like, how do we identify, how do we identify intermediates and catalysts in a multi-step mechanism? Okay, you're gonna know something is an intermediate because it gets produced, then consumed. So it's not gonna be in the overall reaction. So for example, if I have A plus B making C plus, no, let's just do A plus B makes C. And then C plus D making E. Do you guys see how C is getting produced and then consumed, right? So it would cancel out. And really my overall reaction, if I were to add up these two reactions, oh, I ran out of room. That's sad. My overall reaction would be A plus B plus D is making E. So if something gets produced and then consumed, it's an intermediate. Okay? And sort of the opposite of that is a catalyst. So a catalyst is something that lowers this activation energy of your rate limiting step. So like if I was looking at this reaction and it was catalyzed, I would lower that activation energy. It would drop down. And so that reaction would happen faster. And we can identify catalysts because a catalyst is present at the beginning at the start of reaction and at the end of the reaction. So it like bonds to the reactants. It either blocks off, bonding sites, or it helps change the orientation of the molecules so that the collisions are more effective. You can think about catalysts as, enzymes are catalysts. So you think about that in terms of biology. And then they pop back off at the end of the reaction. So they're not, part of the reaction. They're present at the beginning and they're present at the end. So they would cancel out. So for example, if we had if we had A plus B making C, and then C plus D making E and A. See how A is present at the beginning and it's present at the end? This would be a catalyst. It's present at the beginning and it's present at the end, but it would not be present overall in the reaction. So in this case, A is the catalyst and C is the intermediate. It's getting produced and then consumed. So that would cancel as well. So here my overall reaction would be B plus D making E. Okay, so be able to identify in these mechanisms whether something is a catalyst, present at the beginning, present at the end, or whether it's an intermediate, produced and then consumed. Yay, I did it. I only went 1 minute over. All right, I'm gonna stop recording.